Hello everyone. We've been talking about autoencoders and how they can reduce the dimension of our input and basically compress the input. And now I showed you how to throw convolution into the mix so we can have convolutional layers which make a lot more sense for data with spatial coherence like images. And now I want to talk about how to organize the latent space a little bit better because we did okay here with the deep convolutional autoencoder we were seeing. These images look pretty good. But I would like to avoid things like gaps in the latent space, because really what I want to be able to do is just draw some random number in the latent space and generate something and be assured that it actually was in the distribution of my data that was learned. So if I generated, x coordinate 0.3 and y coordinate 0.2 here, it seems like I might have a gap in what I covered in my latent space, and I would like to prevent that. So what we're going to do to get more control over our latent space is turn to something called variational autoencoders, which are basically, it's just autoencoders plus Bayes' rule. So now we're going to have some kind of belief over our latent space and also over our variables that we're going to keep track of. So to diagram out what an autoencoder looks like, we have an input x that's higher dimension here, so I'll depict that by the larger vertical line. And then we downsample to some latent space here. So this is our latent space, and I'll call that Z. And then we upsample from the latent space back to the dimension of the input. And actually, for now, I will call that, I'll call that X estimate, X-E-S-T. That's how I've reconstructed X here. Now so far, this describes exactly the autoencoder that I made a moment ago. But what we're going to do now is put some beliefs into this. So now I'm actually going to have a distribution over what I think might be the latent code. So I'm going to write this actually as a probability z given x here. And so now I'm saying, well, I might not just have one latent code for a particular input. I'm actually going to have an entire distribution of confidences of a latent code. And I kind of want it to be like certainly concentrated in one part of the latent space. So for example, I want to have concentration for particular images. So, as an example, I might say, all right, maybe the latent vector 0.5, 0.6 in a 2D latent space, maybe that goes to a digit image that looks like this. I don't know, let me draw, let's say that goes to a 7 or something. So maybe that goes to the 7. And I would like it to be, if I twiddle these a little bit, I want to get something that's not too far from that. So if I instead had the input here being, let's say 0.49, 0.61 or something. Well, it would be nice if that was basically the same image. And so I'm also going to prevent this thing from jumping around too much. So another way to look at that is if I zoom in the latent space here, I kind of expect there to be a little blob where maybe all the 7s are, and then maybe a little blob where all the 5s are. That's kind of the idea. So maybe that particular 7 has the highest probability in the center of this blob, but if I move a little bit in that circle, I still kind of see that 7. And then maybe in a different region of the space, maybe that's a 5 or something, like I said. And so that, I would want that. Maybe the 5 is most likely right in the center of that region, but if I move a little bit, then I still get that 5. That's the idea. Okay, so to emphasize what's really happening with the hidden variables here, let me draw a graphical model to show you how they're related. So really what I'm saying is I have this latent variable, or really a hidden variable is what we've called this in the past when we were talking about hidden Markov models. I have some hidden variable that I'm trying to learn from my observation x. So the graphical model really looks like this. It's that my x really depends on the hidden variable. And so I actually kind of need to flip this around because I might be able to model the dependency from my hidden variable to my x, but what I really want is this posterior likelihood here. I want to know what is the probability of the latent vector given the observation. So to flip that around, I'm going to use Bayes' rule. So I'll say, okay, the probability of z given x is equal to the probability of x given z times the probability of z, all divided by the probability of x. So if we look at this, let me label these different parts. This is a review of stuff we've done before with Bayes' rule. Actually, if I go back to the page just to show you, and I go to class exercises week 4 Bayes' rule, I drew this out in great detail using the COVID example, and I showed this stuff. So you might want to go back and review that quickly. I'll put a link to it in the video. But let's refresh ourselves on what these different terms are here. This is called the likelihood, or the observation likelihood. And so that is the probability that we make this particular observation given that we have this latent vector. So I'll call this the observation likelihood. This is the prior probability of a latent vector. So I'll call it the latent prior. And I'll talk a lot more about that in a moment. But that's actually something we can model, or that we can choose. This is where we get a little bit of control. We can say, this is what I want your latent space to look like. In the absence of anything else, I want your latent space to concentrate in this way, along this probability distribution. And then finally, this is the observation probability. So independently of what the latent vector is, or factoring out the latent vector, this is how likely it is that I would actually see this digit if I were truly modeling a digit. So that would be helpful. Being able to model the observation probably will be helpful when we see how well our x estimate is actually matching the distribution of the input. So that's the framework we're using now. So basically we just, it's Bayes' rule plus autoencoder. So now we're just adding a little bit of uncertainty to what the latent vector is. Or another way to look at it is we're adding some prior information, some probability distributions that we're going to be able to model to get a little bit more control here. All right, so before I go too much further, I need to define something called a Gaussian distribution. This is also known as a bell curve or a normal distribution. And this is a very nice probability distribution that we can use to model beliefs and all sorts of other things. And so the definition of the probability density function for this is something parameterized by two things. We have a mean, I'll call it mu, and then something called a standard deviation, which I'll call sigma here. And so the probability that we're equal to that a random variable takes on a particular value x is equal to 1 over root 2 pi times sigma times e to the negative x minus mu quantity squared over quantity 2 sigma squared. All right, so what is all this? Let's look at that. Okay, so there's the equation. Now let me plot this actually, because what this is going to give a probability density for taking on particular values of x. So if I were to say, all right, let's look at x maybe in the range from -3 to 3. I'll take 1,000 samples of this and I'll look. So they'll say p is equal to 1 over square root of 2 pi. And actually, let me define these variables here. I'll say mu is equal to 0. To start with, I'll say sigma equals 2. Or let's say sigma equals 1. This is called the standard, or Gaussian here. So 2 pi, root 2 pi times sigma in the denominator there. That is called our normalization constant, times exponent of negative x minus mu quantity squared over 2 times sigma squared. So I just literally just translated my equation into code here. So if I look at this, here's what it looks like. And so you might have seen this before. Again, this is called the bell curve. So let me put in the title here what the mu is and what the sigma is, so that we can have this. And have a look at them. So here's mu is equal to 0, sigma equals 1. If I were to change the mu to 1, notice that moves over to the right. So the mu is what we call the mean For the bell curve, it's actually the most likely value of the random variable. And then we kind of fall off and become less probable on either side of that mean. How quickly we fall off is determined by the standard deviation. If I make this smaller, then we fall off more quickly. If I make this larger, then we fall off more slowly. So that means it's more likely to see a 3 with a larger standard deviation here than it is to see a 3 with a smaller standard deviation. Okay, so let me move the mean back to the origin here. I'll make this the standard deviation 1 again. And so actually NumPy and Torch both have a method called randn. So if I look at this in NumPy here, if I say np.random.randn, let's draw 100 numbers. This is going to give me a bunch of numbers. And if I look at a histogram of those numbers, let me take even more. Let's take like 1,000. And I'll say, let me take the bins. Let me make the bins from, well, let me make the bins the same as what X was here. So actually I better take a lot more samples. Okay, yeah, so that's kind of it there. So here is a histogram. Actually, and let me say, I'll just say linspace from -3 to 3, maybe just 50 samples. Okay, that's fine. So here is a histogram of what I got out of that method. And that looks a heck of a lot like this distribution, and in fact it is. So what NumPy randn has done is it's actually sampled a bunch of numbers according to this distribution. So it's the most likely that you're going to be 0, and you get less and less likely as you go away from that. Now, I can actually shoehorn this method into doing something a little bit different. If, by default, this is going to return variables distributed with mean 0 and standard deviation 1. But if I want to change the mean, what I can do is simply add what the mean is to this. So let's say that I wanted to shift over the mean to 1. So that shifts over. So I simply add 1 to the outputs of this. You see that shifted over. And if I wanted the standard deviation to be different, let's say maybe I wanted the standard deviation to be a little bit smaller. Let's say maybe 0.5, so that gets a little tighter there. Or let's make it really tight. Let's make it like 0.1. So very tight there. What I can then do is simply write this as sigma times the output. So I just multiply the outputs of NumPy's standard mean 0 sigma 1 by what I want my sigma to be, and then I add the mu. So this is called, people get very fancy about this, they call this the reparameterization trick. Okay, so it's just, if I know how to sample from a standard Gaussian with mean 0, standard deviation 1, I can always sample from any other Gaussian that I want. So that's great. The other thing that's kind of cool about this is, let's say that I have, suppose I have more than one variable. Suppose I have multiple variables that are independent, we'll say independent and identically distributed, or IID for short. Now, IID, that's a funny acronym, that also stood for Information Initiative at Duke, which is where I worked as a PhD student, and I don't think that was a coincidence. I think that was a clever pun. But anyway, this assumption is used quite often. So what we could say is, we have these two variables, maybe x and y, which both have the exact same distribution. So if I were to take this probability and assume that I had a variable in x and a variable in y that were independent, what I could do is just multiply those probability distributions together. So I'll do a broadcast multiply here, and I'll show you what it looks like. So if I were to look at this as an image, and actually let me get to a bigger standard deviation again here. Maybe I'll say 0.5, and I'll move the mean back to 0 again. So if I were to look at this, then I would see this kind of an image. And let me get my labels here right. So this was x0, x-1, x-1, x0. Okay, so just to get the labels right here. So this is now, I'm saying I have two variables. So x and y perhaps. And they each have the same distribution. So they each have this Gaussian distribution with mean 0, standard deviation 0.5 is what I think I made. So it's like taking this as a function of x and multiplying it by the same kind of function as a function of y. And then I get this blob. So a two-dimensional Gaussian is a blob. So if we go back to some of the probability distributions that we have here, what we can do is, first of all, make the latent prior be distributed as, so this is the notation I would say, a Gaussian with mean 0, standard deviation 1 in each dimension. So I'll have each dimension independently and identically distributed as the unit Gaussian. And so what I'm saying is, yes, indeed, I want the blob to be my prior. I want, knowing nothing else, I want to construct my latent space so that it concentrates around that blob. The other thing I want to do is I'm going to make the form of the posterior. So the estimate that I'm actually looking for here. So this is what the encoder would do. So the encoder is actually going to encode a probability distribution through this posterior likelihood. That's what it's called. And what I'll do there is I'll actually have the encoder learn the parameters for each dimension there. So I'll say p z sub I given x is distributed as, oops, it's not equal, it's just, this means distributed, probability distribution, as these learnable parameters. So, mu I given x and sigma I given x. So we're actually going to learn a mean and a standard deviation for each x, and we're going to say, hey, this is distributed as a Gaussian. So it's exactly like I drew down here. It's like, given an x, here is my distribution on what the latent code should be. It's like a little blob. Each dimension is independently a Gaussian with this mean and this standard deviation that depends on the input. Okay, let me see if I can code this up now. I just copied and pasted the autoencoder code that I already had, because it turns out I just need to make a few little tweaks. So if I get down into it here, I am going to now, instead of just encoding the latent space directly, I'm actually going to, for each dimension, encode both a mean and a standard deviation. So now, instead of just, okay, so I'm going to do something a little different here. I am not going to do this right away, so I will flatten. But I'm going to wait a second on the linear layers, and actually I'll make, so this encoder is just going to go down to 512 dimensions or whatever, what it is flattened before I go to the latent. And what I'll do is create a linear layer for both mu and sigma. So I'll say, okay, self.mu is equal to torch.sequential, or nn.sequential. So we'll do a linear going down from that flattened dimension to the latent. So we'll have a mean for each one of these. And actually for the mean, I don't want to have any restrictions on just being positive. I think for the mean, I will say, let's do a tan H activation. So that is, unlike a sigmoid, which is between 0 and 1, that's going to keep me between -1 and 1. We'll try that to start with. And then I'll have an encoder for the standard deviation, sigma. And in that case, yes, there's just as many sigmas as there are mu's. In this case, though, I'm going to use a ReLU. I don't want this to be negative. It only makes sense if my standard deviation is non-negative. Okay, so that's the only change you need to make there. Now when I go to encode this, I'm going to say, okay, first the encoder gives me the flattened dimension. Then I want to estimate mu from that flattened dimension. So I'll say mu is equal to self dot, and let me make this a little clearer. This is the mu encoder. This is the sigma encoder. So mu is equal to the mu encoder of flattened dimension, and sigma is equal to self dot sigma encoder flat dimension. And then what I need to do is So once I've estimated mu and sigma, I can use the reparameterization trick to sample a z in the latent space. So I have these parameters that are telling me that, okay, yeah, the distribution of your latent given this x is supposed to be in this little disk here. And I want you to randomly draw some sample that you know, according to that probability distribution. So chances are I'll be more towards the center of this disk. But I'm gonna have a little bit of randomness there. So I'll say z is equal to mu plus sigma times, and now I gotta make a random number. So I'm using my reparameterization trick. I gotta say torch dot rand n sigma dot shape. And one little tricky thing you have to do here is you gotta send, when you generate a new tensor, it comes back on the CPU. So you gotta send it over to the same device as whatever tensor you're element-wise multiplying that back by. Okay, now the decoder can stay the same. The decoder is just going to take the latent sample and it's going to generate its best guess. Now it turns out that the loss actually we're going to need to do something with. So what we're starting with here is the fit to the data. So we want our output to look like the input to the autoencoder. But we need another term because, yes, we want to fit the data, but we also want to fit the prior. And so I've coded this ahead of time. I'll do a derivation of this in the next video. But for now, let's just look at what this is. So keeping in mind that the prior is supposed to be a Gaussian with mu equals 0, sigma equals 1 over each dimension. If I look at the sigma and the mu that were estimated for this particular latent encoding, I see that, well, if mu is 0, so if I'm matching this perfectly, if mu is 0 and sigma is 1, I look at this, that's 1 plus 0 minus 1, which is 0, minus the log of 1, plus a tiny number to prevent some numerical problems. So this whole thing should be 0 if I match the prior exactly. It turns out if I do not match the prior exactly, this will grow away from 0, and I'll try to prove that in the next video. So this will actually be positive if I'm not actually matching the prior for this particular latent vector. So yeah, it's kind of interesting. I don't want them all to be in the center, right? but somehow, it's a trade-off. I'm saying, well, I want you to match the prior, but I also want you to match the data. And so I have two components for the loss. So let me go ahead and return both of those. And I will try to modify the code here. So I will say, okay, yeah, now I'm returning two components from the loss, the loss due to how well I'm fitting the data, and then the loss due to how well I'm fitting the prior. And to start with, let me just add them both together. But I'm going to play around with this a little bit. I'll just make sure the code runs. Okay, the code runs. Now give me a second. I'm going to edit this, and I'm going to save away the loss fit and the loss prior, and we're going to experiment with this a little bit. Okay, so I went ahead and made a few little changes here. One thing I actually decided to do was to multiply the mean by 5, because the hyperbolic tangent has a range between -1 and 1, but I want to give it a little bit more flexibility to move around just to prove a point. So I'm going to make the range actually be between -5 and 5 of the mean there. The other thing I did was I defined this variable called lambda, because what I want to do is play with the trade-off between the fit loss and the prior loss. But first, I'm going to start off with lambda equals 1, just to see what happens when I add them directly together. So I ran this for 11 epochs, and here's what I got. And actually, the fit here looks quite good, but I wouldn't really say that this looks like a blob. This doesn't look like the prior that I wanted it to be like that. And so if I look at the loss terms, I see that, well, the fit loss is much bigger than the prior loss. So the prior loss doesn't really seem to have weighed in much here. So let me try to increase lambda by a factor of 100. So let me go up and I'll make the prior loss much more important. And so this would actually be like saying 36 plus 45 in that case. So the lost prior would be worth a lot more, although I'll report it as it is originally, just so we have a direct comparison. So let me go ahead and run this again and see what we get. Okay, so looking at the results now, it's much clearer that they're distributed among this isotropic Gaussian with mean at the origin and standard deviation of 1. But unfortunately, we don't have as good of a fit to the data. So it seems like we can see there is a bit of a trade-off. So going back to the original where I had lambda 1 and I wasn't putting as much of a penalty on not matching the prior. Had a lot more gaps here. This didn't really look like a blob as much. But when I made that higher, I had a higher loss to fitting the data. So I wasn't as faithful to the data, but I was more faithful to the prior. That looks more like a blob. So let me choose something in the middle. Let's say like maybe a lambda of 30 or something. So let me give that a row and see how that turns out. All right, so here's the results, and they look quite nice. So you notice that the data is fit better. So this is what we had before when we were paying a little bit too much attention to the prior. This time we still look like a blob, but the data is fit better. And if I compare that to the other extreme where I wasn't really paying attention to the prior, you see there's much bigger gaps here. Whereas here you can see, especially towards the center, this is matching the prior distribution pretty well. So I don't see too many gaps, and I'm pretty confident that I'm packing my data in there. So good, there we are. And what I'll show you in a moment is how to derive this crazy equation that we had up here for expressing the fit of the prior. So I will derive that from first principles.